Hello friends, in this episode of Science Physics, we'll learn about motion of the wheel. A wheel is a circular ring that is designed to rotate on its axle. Wheels are used for many purposes, such as in vehicles to reduce the force required to keep them moving on a surface. They are also used on machines to transmit rotational motion and to change the direction of a force. You might have seen a bicycle, tricycle, or a car. All these vehicles move with the help of wheels. So, wheels play an important role in our lives. Let us take a wheel and fix it on a stand. Now, let us roll it on a flat surface. Observe how the wheel moves. The wheel makes contact with the floor at one point. This point is known as the point of contact. When we roll the wheel forward, the point of contact moves to the right. As the point of contact moves, the position of the wheel changes. After some time, the wheel completes one rotation and returns to its original position. This motion of the wheel, where it moves along a straight path by rotating on its axis, is called rolling motion. When the wheel rolls on a flat surface, there are three types of motion present. They are translational motion, rotational motion, and oscillatory motion. Translational motion is the motion of the center of mass of the wheel along a straight path. Rotational motion is the motion of the wheel around its axis. Oscillatory motion is the periodic motion of the wheel from one side to the other side about an axis. Rolling motion can be explained as the combination of two motions. These are sliding motion and pure rolling motion. Sliding motion is the motion of the point of contact along the surface. Pure rolling motion is the rotation of the wheel about its axis. If we closely observe a wheel rolling on a flat surface, we find that the bottommost part of the wheel remains at rest, and the upper part moves in a circular path. In pure rolling motion, all parts of the wheel from top to bottom move with the same speed. As a result, the wheel makes one complete rotation in 1 second, and hence the angular velocity of the wheel is equal to the frequency of rotation. If we consider the center of the wheel, it appears to be moving along a straight line, and hence the linear velocity of the wheel is equal to the product of the radius of the wheel and its angular velocity. Let us see how to derive the relationship between linear velocity and angular velocity. When a wheel rolls on a flat surface, let r be the radius of the wheel and v be the linear velocity of the center of the wheel. Let omega be the angular velocity of the wheel. If we consider a small element of length ds on the rim of the wheel, then the linear velocity of this element is equal to the product of the radius of the wheel and its angular velocity. That is, v equals r omega. The motion of the wheel on a flat surface is periodic. It means the wheel repeats its motion after a fixed period of time. The minimum time required to complete one oscillation is called the period of oscillation. The period of oscillation of a wheel depends upon the mass of the wheel and the force of gravity acting on it. Let us take a wheel and suspend it from its center using a string. When the wheel is at rest, the string is in an unstretched condition. Now, let us give a small nudge to the wheel so that it starts oscillating. Observe what happens. Due to gravity, the wheel falls down on one side. As the wheel falls down, the string gets stretched. At the lowermost position, all the potential energy of the wheel is converted into kinetic energy. As the wheel goes up on the other side, the kinetic energy of the wheel is converted back into potential energy. Then the wheel comes to rest momentarily on the other side. After this, the wheel again starts falling down and the motion continues. You might have observed that during oscillation, the wheel makes a complete rotation in one complete oscillation. The time taken to make one complete oscillation is called the period of oscillation. To calculate the period of oscillation, let us consider a wheel of mass m and radius r. Let omega be the angular velocity of the wheel at any instant. Let h be the vertical height of the center of mass of the wheel from the mean position. Then the potential energy of the wheel at this instant is mgh. Here g is the acceleration due to gravity. At the mean position, all the potential energy of the wheel is converted into kinetic energy. Hence, the kinetic energy of the wheel at the mean position is mgh. Now using the conservation of energy, we get 1/2 I omega squared equals mgh. The net force acting on the wheel is equal to the product of the mass of the wheel and its acceleration. That is Fmg sine theta equals ma, where F is the force applied on the wheel and m is the mass of the wheel. Substituting A equals alpha r in the above equation, we get Fmg sine theta equals mr alpha. The torque acting on the wheel is equal to the product of the moment of inertia of the wheel and its angular acceleration. That is, Fr equals 1/2 mr squared alpha. For a wheel, the moment of inertia is given by I equals 1/2 mr squared. Substituting I in the above equation, we get Fr equals 1/2 mr squared alpha. Solving for alpha, we get alpha equals 2ar. Substituting this value in the equation, Fmg sine theta equals mr alpha, we get Fmg sine theta equals 2 meters a. From this equation, we can see that the acceleration of the wheel is given by A equals Fmg sine theta, 2 meters. The linear velocity of the wheel is given by V equals r omega, and the acceleration is given by A equals alpha r from these equations. We can see that the linear acceleration of the wheel is equal to the product of the angular acceleration and the radius of the wheel. The kinetic energy of the wheel is given by K equals 1/2 I omega squared plus 1/2 mv squared, where I is the moment of inertia of the wheel about its axis of rotation. For a wheel, the moment of inertia is given by I equals 1/2 mr squared. The kinetic energy of the wheel is K equals 1/4 mr squared omega squared plus 1/2 mv squared. As the wheel rolls up the incline, the kinetic energy of the wheel is converted into potential energy. Hence, the potential energy of the wheel at the final position is equal to the initial kinetic energy. That is, mgh equals 1/4 mr squared omega squared plus 1/2 mv squared. Here h is the vertical height of the center of mass of the wheel from the initial position. From this equation, we can see that the potential energy of the wheel is directly proportional to the square of the angular velocity of the wheel. Let us now derive the equation for the period of oscillation. The period of oscillation is the time taken to complete one oscillation. It is given by t equals 2 pi omega. Substituting omega squared equals 2 GARD r, we get t equals 2 pi root r, 2 grams. Therefore, the period of oscillation of the wheel is inversely proportional to the square root of the acceleration due to gravity. When the wheel rolls on an inclined plane, the period of oscillation of the wheel depends upon the angle of inclination of the plane. When the angle of inclination of the plane is increased, the period of oscillation of the wheel decreases. That's all for today. See you next time.